Namaste. Welcome to the next video of Machine Learning Practice course. In this video, we'll study how to handle large-scale datasets in scikit-learn. In this course, so far, we were able to load entire data in memory and were able to train and make inferences on all the data at once. The large-scale datasets may not fit in memory and we need to devise strategies to handle it in context of training and prediction use cases. Large-scale datasets is what you will encounter in many of the real-life applications of this age. There is explosion of data that different companies are collecting from their customers, from their processes, from manufacturing units, from different devices. And in order to train machine learning models on this large-scale data, we need special handling of the data, the feature generation process, and the training process. Fortunately, scikit-learn has some functionality for handling large-scale datasets. And the topic of this video is to understand what kind of tools that are available to us in order to perform large-scale learning with scikit-learn. In this topic, we'll discuss tools available in scikit-learn for large-scale learning. We'll discuss overview of handling large-scale data, incremental preprocessing and learning, basically fit versus partial fit. So far we were using fit function for training the model. Now partial fit will be our friend when it comes to large-scale datasets. We'll provide a short demonstration for combining preprocessing and incremental learning towards the end of this collab. So large-scale machine learning differs from traditional machine learning in the sense that it involves processing large amount of data in terms of its size or number of samples, features, and classes. There were many exciting developments in efficient large-scale learning on many real-world use cases in the last decade. Although scikit-learn is optimized for smaller data, it does offer a decent set of feature preprocessing and learning algorithms such as classification, regression, and clustering for large-scale data. So one way to check whether there is a support for large-scale dataset in a given estimator or any other preprocessing functions in scikit-learn, you should check whether that particular API has partial underscore fit method. If there is a partial underscore fit method, there is a good chance that that API will support large-scale learning. So scikit-learn handles large-scale data through partial fit method instead of using the fit method. So what is the central idea? The central idea is to process data in batches and update the model parameters for every batch. This way of learning is referred to as incremental or out-of-core learning. So you can see here that we cannot fit the entire data in memory and call the fit method. So what we'll do is we'll load as much of data as we can in memory and we'll use partial fit method for that. And what partial fit method does is it loads a batch of data in memory and performs the parameter estimation. Then it loads the next batch in memory and updates the parameters of the model. And it keeps doing it until it processes the entire data. So the incremental learning may be required in the following two scenarios. One is for large datasets or out-of-memory datasets where it is not possible to load entire data into the RAM at once. So one can load data in chunks and fit the machine learning model for each chunk of the data. And there is another use case for machine learning task where a new batch of data comes with time. So retraining the model with previous and new batch of data is computationally expensive process. So instead of retraining the model with the entire data set, one can employ an incremental learning approach where the model parameters are updated with the new batch of data. So let's look at the incremental learning support in scikit-learn. To perform incremental learning, scikit-learn implements partial underscore fit method that helps in training an out-of-memory dataset. So in other words, it has the ability to learn incrementally from the batches of instances. In this collab, we'll see an example of how to read, process, and train on such a large dataset that cannot be loaded in memory entirely. The partial fit method is expected to be called several times consecutively on different chunks of dataset so as to implement out-of-core learning. This function has some performance overhead, so it is recommended to call it on a considerable large batch of data to overcome the limitations of overhead. So let's look at the attributes of partial fit method. So partial fit method takes feature matrix, label vector, the list of classes and sample weights as inputs. List of classes and sample weights are optional, but it is recommended that we supply the list of classes very first time when we call the partial fit method. That enables the partial fit method to have the complete list of classes, because since we are processing the data chunk by chunk, it may happen that in the first chunk certain examples from certain classes might be missing. So the following estimators in scikit-learn implement partial fit method. As far as classification is concerned, multinomial naive Bayes, Bernoulli naive Bayes, HGD classifier and perceptron implement partial fit. And you know that with HGD classifier we can implement different type of classifiers by changing the loss function. HGD regressor also implements partial fit and it can be used for large scale regression problems. And for clustering, this is a topic that we will be studying later in the course. There is a mini batch k-means that also implements partial fit method. So HGD regressor and HGD classifiers are commonly used for handling large datasets. Now you may remember our discussion of gradient descent, batch gradient descent and stochastic gradient descent. So any algorithm that uses, let's say, full batch gradient descent, something like support vector machine, random forest, of course we have to discuss these algorithms, they will be coming in subsequent weeks. So one of the limitations is that because they're using full batch gradient descent, they need to load all the data in memory before performing any learning. And when we are working with large scale dataset, loading all the data in memory is not an option because it is just not feasible. On the other hand, HGD, if you remember stochastic gradient descent, updates the model parameter with a single example. Or even mini batch gradient descent uses a small number of examples to update the model parameters. And the way HGD classifier and regressors are implemented is that there is a facility to provide the number of examples as arguments in HGD classifier and regressor. So HGD can deal with large data sets effectively by breaking up the data into chunks and processing them sequentially. So for HGD, we need to load only one chunk into memory at a time, and HGD updates the model parameter with that chunk and then goes to the next chunk. So this is very useful for handling large data sets and also the data that comes in intervals. So far what we have studied is that there is a partial fit method that helps us to handle the large datasets, and possibly HGD is another powerful method at our disposal for handling large datasets. Let's look at practical example of fit versus partial fit. So here what we do is we will be using HGD classifier for a classification problem on a synthetic dataset, and we will show the use of fit and partial fit and show that both fit and partial fit leads to similar kind of results. So we first import the necessary libraries like HGD classifier, then the dataset creation with make classification API, Then we also import train test split in order to split the dataset into training and test. Then confusion matrix and classification report for evaluation of the model. So what we'll first do is we'll use first fit, but before that we'll generate a sample dataset that has got 50,000 samples with 10 features. And there are 3 classes. So after generating the dataset, we split the data into training and test. So we set aside 15% examples for test. We make use of HGD classifier with maximum number of iterations set to 1000 and tolerance set to 0.01, and you may recall that tolerance is used for deciding the convergence of the HGD classifier. We'll be using traditional fit method to train our model. So here we simply call the fit method with the training feature matrix and training labels, and we train our HGD classifier. So we obtain the score of 0.87 on the training dataset. And on test data, we also obtain very close test score as with the training score. Both the scores are 0.87. We look at the confusion matrix and classification report on the test set, and we obtain, you can see that we obtain the F1 score of 0.90 for class 0, 0.83 for class 1, and 0.88 for class 2. So overall accuracy is 87%. Now what we'll do is we will use partial fit method instead of fit method. So here we generated the training data and use fit method, and this is what we have been doing so far in this course. Now the change would be that instead of fit we'll be using a partial fit method. So you may recall from our discussion that partial fit basically loads a small chunk of data in memory, processes them, and in processing what it does is it actually trains the model on that chunk of data. Then it loads the next chunk and update the model parameters. So this is how partial fit method works. So what we'll do is we'll pretend that this dataset that we have generated, which has got 50,000 sample, is we just cannot load the entire data in memory. So what we'll do is for that we will load this data in chunks in memory and then call the partial fit method for training the model. So let's see how to do that. So we first concatenate the training feature matrix and training label into what is called as train data, and we store this train data into a CSV file. Now the data is in the file, and what we'll do is we'll read this file chunk by chunk and call the partial fit method. So we instantiate an HGD classifier with maximum iterations set to 1000 and tolerance set to 0.01. And this is where we are processing data chunk by chunk. So we are going to use the read CSV function in pandas that has got attribute called chunk size, and this chunk size parameter specifies the number of rows per chunk that we want to read. So here we set the chunk size to 1000. So we are going to read 1000 examples at a time and then call the partial fit method on those 1000 examples. So remember that while performing or while calling the partial fit method for the first time, we need to also supply the list of classes that we have done here. That's why we have a conditional statement here. So if the iteration number is 1, then we call partial fit with the list of classes. And for the subsequent iterations, we do not need to specify the list of classes, and we simply specify the feature matrix and label vector. And after every iteration, we are printing the coefficients and the intercepts that are that are obtained by the partial fit method. So here you can see that after every iteration we are printing the intercept. So there are three classes, so there are three intercepts and there are three weight vectors, one per each class. So you can see that after every iteration the weight vector is kind of changing and also the intercepts are changing. Now after the training is complete, we obtain the score on the test set. It is 0.82, which is lower than what we obtained from the fit method earlier. And F1 scores are also slightly lower than what we obtained earlier. We obtained F1 score on the class 0. The F1 score is 0.88, for class 1 it is 0.77 and for class 2 it is 0.83. The overall accuracy is 82%. So this was a small demonstration of how to use partial fit method instead of the fit method. So apart from HDD classifier, we can also train perceptron, multinomial naive Bayes and Bernoulli naive Bayes in a similar manner. So far we have seen how to train a model in stepwise manner. Now we will see how to perform preprocessing in stepwise or in incremental manner. So here we show couple of preprocessing techniques, which is CountVectorizer and HashingVectorizers. So vectorizers are used to convert a collection of text documents into a vector representation. So this is a preprocessing step mainly in case of text data. So CountVectorizer and HashingVectorizers both perform task of vectorizing the text document. There are some differences between them. So one difference is that HashingVectorizer does not have or does not store the resulting vocabulary. Hence it is used to learn from the data that does not fit into the memory. So each mini batch is vectorized using HashingVectorizer so as to guarantee that the input space of the estimator has always the same number of dimensions. With HashingVectorizer, each token directly maps to a predefined column position in the matrix. So for example, if there are 100 columns in the resultant matrix, each token would get mapped to one of the 100 columns. The mapping between the word and the position in the matrix is done using hashing. So as the name suggests, it's HashingVectorizer. So hashing, which is a technique that you must have studied in the data structure, is used for generating a vector representation for the text data. So HashingVectorizer, what happens is each token gets transformed into a column position and we do not really maintain a vocabulary. And not storing vocabulary is very useful while handling large datasets because we just cannot hold a huge token vocabulary comprising of millions of words into memory since the memory is limited. So since HashingVectorizer does not store vocabulary, it doesn't take much space unlike the CountVectorizer. So it also alleviates any dependency with function calls performed on the previous chunk of data while performing incremental learning. So HashingVectorizer is kind of another friend of ours when processing large-scale text datasets. So now what we'll do is we'll take some sample text documents and vectorize them using both CountVectorizers and HashingVectorizers so that you get an idea of how both these vectorizers work. So these are 4 small text snippets, and what we'll be doing is we'll be first using a CountVectorizer, and CountVectorizer is a preprocessing technique and it is part of scikit-learn.feature_extraction.text module. So we instantiate a CountVectorizer and then call fit_transform method. Now remember that this is a preprocessing technique and each preprocessing API has fit_transform method implemented. So we pass the list of text documents to the fit_transform method and we obtain a transformed representation or the vector representation of the documents. So you can see that the shape of the the feature matrix is 4 by 66. So 4 is the number of text document and 66 is the size of vocabulary. There are 66 unique tokens in these 4 documents. So here the vocabulary is present in the dictionary format, where the key of the dictionary is a token and the value is the ID assigned to this particular token. So 000 has the ID 0, 122 has ID of 1, 150 has the ID of 2, and so on. So we have 66 such kind of tokens, and we have assigned IDs from 0 to 65. And you can also see that these tokens are in alphabetical order. So let's see how the text documents are represented. So this is our text documents, 4 text documents, and we'll see how they are represented with CountVectorizer. So we have what is called as a sparse matrix representation. So we do not show, or we do not store all the 65 dimensions for each tokens, because not all 65 tokens will be present in a document. So we only store the index of the tokens or index of the words that are present in the document. For example, document 1 has got word or token with index 54. We can check it out. What is the 54th token? It is the word the. So this word the has come 3 times. We can go here and actually check whether the has come 3 times. There is one the here, second the here, and there is a third the over here. So indeed the has come 3 times in the first document, and hence you can, so this is the count of the word the. In the same way, the word 62, the word ID 62, which is word well, has come once in the document, which we can go back and check again. So there is word well that has come once in the first document. So you can see that count over here, and so on. So this is how the documents are represented. This is a sparse matrix representation where we only store the indices of words as part of this representation. So similarly, we have the representation for the second document, then for the third document, as well as for the first document. And so we are not actually showing the entire representation, because this listing would be too big. So only few words in the second documents are shown here. Now let us use HashingVectorizer instead of CountVectorizer for vectorizing the documents. So here we import the HashingVectorizer from scikit-learn.feature_extraction.text module. So we'll instantiate an object of HashingVectorizer class. There is an important parameter which is n_features that declares the number of features in the output feature matrix. We set it to 50. Now remember that do not set too small or too large number over here. Too small number will cause hash collisions and which will pollute the representation. But if you set this to a very large number, it will cause large number of feature dimensions for each text document. Now let us perform HashingVectorizer with fit_transform method. So we call fit_transform method on HashingVectorizer by supplying the text documents. Let's examine the shape of transform feature matrix. So there are 4 documents, and each document is represented with 50 values, and this 50 is equal to the n_feature attribute that we had specified. So this is a sample representation for the first text document. So for every text document we get a score from the hashing vectorizer. So overall, hashing vectorizer is a good choice if we are falling short of memory and resources, or we need to perform incremental learning. However, CountVectorizer is a good choice if we need to access the actual tokens. Now in the final section of the collab, what we'll do is we'll combine the preprocessing and fitting in incremental learning. So here we'll be using hashing vectorizer along with HDD classifier. So now what we'll do is we'll work on a small text classification task, which is sentiment analysis or sentiment prediction. So for that, what we'll do is we will represent each document with CountVectorizer, and then we'll be using HDD classifier to detect or to classify the sentiment in the text document. And we'll perform both hashing vectorizer and HDD classifier in incremental manner. So here we download a dataset from UCI machine learning library. So instead of downloading, unzipping and reading, we directly read the zipped CSV file. For that, we are using urllib.request.url open, and then we also use bytes.io and text.io wrapper class to get the data. So there are two columns in the data, which is the review and the sentiment. So let's explore the dataset a bit. So you can see that there is a sentence in the review which is good case, excellent value, and the sentiment is 1. Then the second statement is great for the jawbone, sentiment is 1. Third one is tied to charger for conversations lasting more, and this sentence is not complete here right now, and the sentiment is 0. The mic is great, the sentiment is 1, and so on. So there are in all 999 reviews and 999 sentiment, 1 sentiment per review. And the sentiment is either 0 or 1, 0 meaning the negative sentiment and 1 meaning the positive sentiment. Now we split the data into training and test set. We have 799 examples in the training. Since the data is in the text form, we need to vectorize it, and in order to perform the vectorization in an incremental manner, we use hashing vectorizer. So we instantiate an object of hashing vectorizer, and then we create an instance of HDD classifier with L2 regularization, and here we are using hinge loss. So this way of using HDD classifier with hinge loss, we basically get the SVM, which is the technique that we are going to learn in the next week. Now what we'll do is we will first perform the vectorization of the document. So here we have 799 samples. We can very well use the fit method, but since we are trying to demonstrate the partial fit method or incremental learning, we'll assume that we do not have sufficient memory to handle all 799 samples in one go. So what we'll do is we'll first take 400 samples from the training data and perform partial fit on those 400 samples. Alternatively, we can also think that we only have 400 samples available at a time, and we fit our classifier with these 400 samples, and then whenever more samples will be available, we'll basically update our model. So partial fit is also useful in such a scenario. Now we first perform the transformation on the text document using CountVectorizer, and then we call the partial fit on the on the transformed representation. So we perform the transform feature matrix and the labels along with the list of classes. So while performing the evaluation, we first transform the test set using the same CountVectorizer and call the score method on the classifier object by supplying the transform test representation along with test labels, and we obtain the score of 0.70 on the test set. So this is using first 400 examples. Now what we'll do is we will use the remaining 399 examples and perform the second round of partial fit. So here, this is the second part of the training data. We transform our documents with HashingVectorizers and then perform the partial fit with HDD classifier. After training the data, we evaluate it on the test set, and now you can see that our test accuracy has gone up to 0.76. In this video, we discussed how to train machine learning models on large datasets. We mainly use technique of incremental learning through partial fit method. Any estimator and transformer implementing partial fit method can be used for large-scale learning. We demonstrated working of large-scale learning with sentiment classification example. Now you have tools for solving real-world large-scale learning problems.